So in this problem, we know that x is uniformly distributed between 0 and 2, and it is transformed into y according to a continuous transformation function, which is x over 1 minus x whole squared. And what we are asked is to find the density of y, which is small fy of y, and also plot it. So let's begin with the first part. So we know because x is uniformly distributed between 0 and 2. So if this is x, this is fx of x, 0, 1, 2. We know that this density will be a rectangular function with a height of 1/2 to make the area 1. So this is 1/2 here. And next we can draw this transformation just below this curve to make it easier for us to follow. So again, x 0, 1, 2 here, and this is our transformation y. So now when x is 0, if we substitute 0 here, we just get 0 over 1 whole squared, which is just 0. When x is somewhere in between 0 and 1, let's say 0.5, we have 0.5 over 1 minus 0.5, which is just 1 whole squared. So we have a positive value here. And when x equals to 1, this goes all the way to infinity because the denominator becomes 0. So the curve looks something like this. Now when x is between 1 and 2, the numerator is positive, the denominator is negative, but because we have a whole squared, so we'll have some positive value. And when x equals to 2, the numerator is 2, denominator is negative 1, so the squared will be 4. So we have some positive value here, and the curve looks like this. And this point here is 4. All right, so now we see that if we draw a line y equals to small y, we can have two possibilities. So let's say if the small y is here, you have two intersection points with the transformation. If y is between 0 and 4, let's say here, we will just have one intersection, and this point is here. So so basically we will have these 2 points intersecting the curve, and let's call this point x1 and this point x2. And now just to find the density, we know that the formula to find fy of y, if there is a continuous transformation of y from x, is simply the sum over I, where I is the number of intersections with the line y equals to small y, times fx of xi times dxi over dy. So so now we have two cases. If y is between 0 and 4, our fy will be fx of x1 times dx1 over dy, absolute value here. And if y is bigger than 4, then our fy of y will be fx of x1 times dx1 over dy plus fx x2 times dx2 over dy. So the key idea here is to find fx of x1, fx of x2, and dx1 over dy, and dx2 over dy. So let's see what these points x1 and x2 are. So we know, they are the x values corresponding to the y being equals to small y. So that means using this transformation, we write y equals to x over 1 minus x whole squared, which means plus minus square root of y equals to x over 1 minus x, and that goes on to become plus minus y minus plus x square root of y equals to x. So we're just trying to isolate x here. So this turns out to be plus minus square root of y equals x plus minus x square root of y, which then turns out to be x times 1 plus minus square root of y equals to plus minus square root of y. So from here, basically, x equals to plus minus square root of y over 1 plus minus square root of y. So now it's very clear that your x1 will be square root of y over 1 plus square root of y, and your x2 will be negative square root of y over 1 minus square root of y. All right, so we have got x1 and x2, and remember, when y is here, this point here is also x1, having the same form, x1 equals to square root of y over 1 plus square root of y. And the remaining part is these derivatives. So let's compute these derivatives. So dx1 over dy will be the derivative of this. That means the denominator first times the derivative of the numerator, which is 1 over 2 square root of y, minus the numerator times the derivative of the denominator, which is 1 over 2 square root of y, divided by the denominator whole squared. So it turns out to be, we can bring this 2 square root of y down here. The numerator is just 1 plus square root of y minus square root of y, and this cancels. So it's just 1 over 2 square root of y, 1 plus square root of y whole squared. Similarly, dx2 over dy will be again the denominator times derivative of the numerator minus the numerator times the derivative of the denominator. And this turns out to be, again, 2 square root of y down here, and the numerator will just have negative 1. All right, so we've got fx of x1, fx of x2, we've got these derivatives, and we just need to plug these in to find the solution. So as it turns out, so fy of y will be fx of x1 times dx1 over dy, absolute. And we know fx of x1, from here, just extend these lines upwards, we reach here to get 1/2. Fx of x2, again, will also be 1/2. So this turns out to be 1/2 times dx1 over dy, which was 1 over 2 square root of y, 1 plus square root of y whole squared. For y between 0 and 4, and fy of y was fx of x1 plus times dx1 over dy plus fx of x2 times dx2 over dy for y bigger than 4, which was 1/2 again, 1 over 2 square root of y, 1 plus square root of y whole squared, plus 1/2 times 1 over 2 square root of y, 1 minus square root of y whole squared. So basically, if we write it in a compact form, it will be 1 over 4 times square root of y times 1 plus square root of y whole squared if y is between 0 and 4. And it will be 1 over 4 square root of y, 1 plus square root of y whole squared, plus 1 over 4 square root of y, 1 minus square root of y whole squared if y is bigger than 4. So that's our solution. And the second part here is to sketch this graph. So let's say this is y, this is fy of y. We know we have something different between 0 and 4 and something different for y bigger than 4. So when y is 0, fyy is infinity. When y is 4, if you put 4 here, square root of 4 is 2. So this turns out to be 3 whole squared, which is 9. 9 times 2 is 18. 18 times 4 is 72. So it turns out to be 1 over 72 here if y equals to 4. And this extends all the way to infinity. And if y is bigger than 4, so basically this is included. So for this part here, if y is bigger than 4, then we put 4 here, we get 1 over 72. We put 4 here, we get 9 over 72. It turns out to be 10 over 72. So we will have another, well, let's make this a hollow line here. And then again it decays with y. So if you want to verify this is correct, just integrate this density and you should get 1. That means if you integrate 0 to 4, 1 over 4 square root of y, 1 plus square root of y whole square dy, plus 4 to infinity, 1 over 4 square root of y, 1 plus square root of y whole squared, plus 1 over 4 square root of y, 1 minus square root of y whole squared dy. This should give you 1. So that brings us to the end of the solution.